Hi, in this video lecture, we are going to learn the cluster analysis, another very practical analysis technique which could be used in design research. And there are four different approaches to cluster items: hierarchical cluster analysis, partitional cluster analysis, distribution-based cluster analysis, and density-based cluster analysis. And among four, in design research and in social science, these two are much more frequently used. So in this lecture, we focus on the first two analysis methods. The first hierarchical cluster analysis is based on the core idea of objects being more related to nearby, than the objects farther away. Its another name is connectivity-based clustering. Secondly, the partitional or non-hierarchical cluster analysis is a centroid-based clustering. K-means clustering. The K-means clustering is the most typical technique for partitional cluster analysis. So when do we use the hierarchical cluster analysis? We are using this hierarchical cluster analysis in order to group similar observations with respect to a set of characteristics, or to build a tree diagram where the items, such as cases, were viewed as most similar are placed on branches that are close together. For a clustering example, suppose this data is to be clustered using Euclidean distance as the distance metric. The top row of nodes represents data, for example, individual observations, and the remaining nodes represents the clusters to which the data belong. With the arrows, we can estimate the distance or dissimilarity. The distance between merged clusters is increasing with the level of the merger. The height of each node in the plot is proportional to the value of the intergroup dissimilarity between its two daughters. The top nodes representing individual observations are all plotted at 0 height, so the height increases toward this direction. Furthermore, hierarchical clustering can be agglomerative or decisive. Agglomerative indicates that starting with a single element, like this, and aggregating them into clusters. Decisive explains that starting from the complete data set and dividing it into partitions. So this way. From the survey data, which you already have, I think, I have collected 12 products which had at least 3 evaluations. And based on that evaluations on the 20 adjectives, we could cluster these products into several groups. Here you are presented with the 12 products and the score on each adjective of the 12 products. So based on this set of characteristics, we can cluster these 12 products into several groups. For that, you click Analysis, Clustering, and we first try hierarchical clustering. And for the variable, you select the 20 adjectives. And let's draw a dendrogram. And for the method, we use the default method, which is already selected here because it's the most frequently used. Okay. All right. So using the average connection method, we have obtained this chart, and the numbering here is corresponds to the number of items. In the lecture slide, I have placed the corresponding products for you to understand the result better. As I mentioned earlier, the goal of hierarchical cluster analysis is to build a tree diagram where the items that were viewed as most similar by the participants in the study are placed on branches that are close together. The key to interpreting the hierarchical cluster analysis is to look at the point at which any given pair of subclusters join together, join together, join together, join together. So the joined clusters that join again together sooner are more similar to each other than those that join together later. And this tree-shaped structure is called as dendrogram. Dendrogram is a tree diagram frequently used in order to illustrate the arrangement of the clusters produced by hierarchical cluster analysis. One practical aspect of this dendrogram is that you can use it to directly inform how you might organize the clusters or the items. For that, you can take a vertical slice through the tree diagram and see what groupings that create. For example, this dendrogram shows a 3-cluster slice. The vertical line intersects 3 horizontal lines. In this case, Dieterham's calculator seems to be assessed as a quite unique design. We can perform a cluster analysis again after excluding this calculator. Or we have an idea that the initial pool had a strong tendency toward decorating furniture items only. So by adding more electronic devices which are similar to calculator, or the devices or the items which have a modern style, then perhaps this calculator will not be a minority anymore. I a couple of times mentioned the Euclidean distance. Euclidean distance is to calculate the distance between two variables based on the assessment on set of characteristics. But in fact, you will discover that you are already familiar with this Euclidean distance. Remember that you calculate the distance between 2 points in 3-dimensional space. You extract x1 minus x2 and you square and plus the distance between y, and then you square it and you subtract the z distance and you square it, and then you calculate the square root of this sum. When you calculate the distance between this point and this point in x, y, z space, right? Actually, that's how it works here. One thing you should be aware of that is you should check whether variables are measured in different measurements. When X dimension is measured in year scale, while the Y dimension is measured in currency scale, perhaps the variance of Y will highly affect on the other variances. Therefore, you better standardize each differently measured units. But in our example, each of the adjectives had a 5-point Likert scale, so all measurements were measured based on this identical range of a unit. So we don't need to standardize the ratings here in this case. And based on the Euclidean distance, actually you can measure the between distance of each pair of items. So based on the Euclidean distance, actually you can fill in this shaded area, and the other half is actually identical. So how to calculate the Euclidean distance between each pair? It's very simple. Consider that the distance between this typewriter and sofa in terms of fresh, in terms of flamboyant, in terms of sensuous. So you subtract this from that, and then you square it, and then you subtract these two, and you square it, and then again the distance between these two, and then you square it, and you add all, and then you make a square root. That result will be the distance between typewriter and sofa here, or this place. So by calculating the Euclidean distance of each pair based on the assessment on set of characteristics, you can finalize the proximity matrix. And this matrix displays the conceptual distances between items. In particular, the agglomerative algorithm has a base on Euclidean distance. So you cluster items with smaller distance first, and then you add the next, and so on. When you go further in cluster analysis, you should be aware of that there are several different algorithms that can be used in hierarchical cluster analysis. Popular choices are known as single linkage clustering, which uses the minimum of object distances. Second one is complete linkage clustering, and this uses the maximum of object distances. The linkage method I think works best is the one called group average method, which is default in SPSS. But you might want to experiment with some other linkage methods in order to see what the results look like. There is no absolute rule saying one is better than another. Also, the methods will not produce a unique partitioning of the data set, but a hierarchy from which the user still needs to choose appropriate clusters. In addition, you should be aware that the clustering methods are not very robust towards outliers, which will either show up as additional clusters or even cause other clusters to merge. So what will be the answer or guide to choose a proper method? As I said, either you select the most frequently used one in social science study, or, like this example, you perform different methods and you find out a similar trend, and then you take the clustering results, which can cover the most of the clustering methods. In this case, the complete and word methods seems to result similar one, so you better take one of these two methods. And now the second approach in cluster analysis. that is a partitional cluster analysis. The partitional cluster analysis is often actually referred as K-means algorithm or K-means clustering. It runs multiple times with different random initializations. Variations of K-means often include such optimizations as choosing the best of multiple runs. K-means clustering requires the number of clusters in advance, and the number is to be specified. And this is considered to be one of the biggest drawbacks of the partitional cluster analysis. Furthermore, the algorithms prefer clusters of approximately similar size, as they will always assign an object to the nearest centroid. Let's consider these two examples. The first one is showing you a chart. For the confidential reason, I didn't indicate what x and y axis are indicating. The x is actually the student's performance in basic science subjects, and the y-axis indicates their performance in IT majors. And you see a positive correlation. So the one who performed well in basic science courses also performed quite excellent in Department of IT major courses. Okay, that's actually related to correlation analysis. And what we are going to do here with the partition cluster analysis is that when we need to, or when we have to, cluster our students into several groups based on their performance in both categories of subjects. So here, each student had a coordinate of x and comma and y, and x stands for their performance in basic scientific course, and y stands for their performance in ID course. So it's not easy to cluster students where or based on which score, etc. So in this kind of very uncertain case, and still if you need to cluster them nevertheless, then I think the method is helping you to reach the conclusion. And this is another case. Can we extract some key colors based on the RGB value of each pixel? A picture has a dimension of something like 8 by 600 pixels. So entire number of pixels is quite a lot. So 22,000, something like this. So entire number of pixels reaches to 240,000. And each has RGB values. So based on the RGB values of each pixel, we can cluster the pixels into several groups. And if we can find the average point of each group in terms of RGB, then it's technically possible to extract the key colors. Based on each pixel of this digital image, she performed the K-means clustering analysis, and she gave firstly the number of 10 as the number of clusters she intended to have. So based on the cluster centers of each of the 10 groups, she found out 10 colors. So this color should be this one, and so on. And whether you agree that these 10 colors are really representing the color palettes of this painting is a different issue. And when she gave the 15 as the number of clustering, the center point of RGB of these 15 colors are resulted like that, and she made a color palette out of this table. Again, whether you agree with this result is a different issue, and you can contribute with your creative ideas how to validate the result. And let me briefly demonstrate to you how to perform the k-means clustering in SPSS. Suppose that you have the data set like this. Actually, the RGB data of that picture is much larger than this, but I copied only the 30 pixel information here, and then analysis, clustering, k-means clustering analysis. And we consider RGB aspects and number of clusters here. I assign 3, and then it's very practical that you click here, save, and you create actually extra variable that will indicate which group each case would belong. So click the first, and then OK. Let's go back to the data sheet here. So the first color belongs to the second group, and second color belongs to the third group. So in this way, you can perform the k-means clustering analysis, and very quickly you can find the membership of each case. So going back to the partitional cluster analysis, let's look at when we need this analysis. Firstly, when we need to identify relatively homogeneous groups of cases based on the selected characteristics using an algorithm that can handle large numbers of cases. Suppose that you draw a dendrogram of this number of items. It's almost impossible to draw one dendrogram in one A4 size of paper, right? So when you need to handle a very large number of cases, dendrogram is not a clever way to present the clustering pattern of your cases. And secondly, when you already have to specify the number of clusters, and the partitional cluster analysis requires you the number of clusters in advance. So when you have to cluster these people into 4, then you can assign 4 before you perform the partitional cluster analysis. And the k-means clustering is the most commonly used partitional clustering analysis. And unfortunately, I cannot provide you this data. So instead, I present you here how I have analyzed this data using the k-means clustering. And my result is summarized in such a way. I have given 3 to 5 as a number of clusters in advance, and I have concluded that with 4, I could meet some justification. And each group has a central point like this. So 35 of these blue dots belong to the 4th group, and the largest number of students belong to the 3rd group, and so on. And what you can do after the cluster analysis is that you can compare the mean scores of each cluster, and you can analyze whether there really exists a mean difference or not. In this case, each bar stands for each group here. The color of each bar corresponds to the color of clusters here. And the y-score stands for the scores of the basic scientific courses. I can predict that if I perform between group 1-way ANOVA, there might be statistical significant result which means depending on the clustered result, the average score of basic scientific courses have different mean scores. But from the post hoc test, I think there will not be no difference between these two groups. So if I may add my personal opinion, this red group and yellow group have similar feature that both students of both groups were quite poor in basic scientific courses, but students who belong to yellow group were lucky to have moved to ID. So after they have moved to ID, they performed quite well. But this group, they were still quite poor, indicating that perhaps the ID is not their appropriate major, so they could choose something else. Now, if I compare when to use the hierarchical or partitional cluster analysis, simply speaking, when the data are small, so when the number of observations is small, then hierarchical clustering is more appropriate. But when you handle the big size of data, then partitional clustering is more appropriate. So what should be the criteria to say the small or big? I think if you can draw a dendrogram in your paper, then it's small enough. But when you better not draw the dendrogram in your A4 size paper, then it's big enough. That's a very subjective judgment, but I think that's quite adequate criteria to be applicable to judge whether it's small or big. And in hierarchical clustering, the analysis clusters the closest cases together as the result. And you can draw a dendrogram which makes a tree-like structure. But it's difficult to analyze when the data is too big. On the other hand, the partitional cluster analysis adds up a case closest to the cluster center already defined, and is easy and fast in analyzing big data. But the result varies depending on the number of clusters you already given in advance. Regarding the quiz, please perform the factor analysis using this data set and draw your own results. We will share your drawings in the class. So please draw your coordinates with the 12 products allocated within these coordinates. You can draw by hand or you can use Excel. So anyway, we will share all 21 coordinates drawn by yourself. And perhaps you try to analyze this before you come to class. In case you cannot bring your computer to the classroom. So try out different clustering methods and please try to reach your own conclusion. Thank you for your attention.